Good morning and welcome to our Maths Methods Unit 3 revision webinar. We're using the TI-Nspire CX non-CAS since we're working this for Queensland students. My name is Melissa and I'm presenting today with my co-host Shelley Cross. We are looking at a couple of the topics in Unit 3. In particular, I'm going to be looking at the logarithms, so the first part of Unit 3, which is Topic 1, the logarithmic function 2, and then Shelley is going to be looking at Topic 2, further differentiation and applications 2, and Topic 3, integrals. So we're looking at, obviously, how you can effectively use your TI-Nspire when you are doing the Tech Active or the Tech Allowed questions of your assessment. So let's get started. I've got 3 questions that we're going to look at today. Just very quickly, the subject matter in this first topic of the logarithmic function 2 that I'm focusing on is, if we look at it here from the syllabus, the log laws, so establishing and using the log laws. So you will have completed those in Unit 3. So we're going to look at a couple of questions that use those. We're going to then look at a question that uses logarithms and applies them. So it actually states here to interpret and use logarithmic scales such as decibels in acoustics, the Richter scale for earthquake magnitude, octaves in music, and pH in chemistry. So I'm just going to look at one question today that is an application one. So it's actually going to be octaves in music, but there will also be in the Google Drive, you'll get access to the Google Drive, some extra documents in that after this session. And I've put a couple of questions in there. One that is, another one that's decibels, one that is the Richter scale, and one that is a pH question as well. So we'll be providing you with those revision questions after the session today, and we will also provide you with solutions to those. So we're going to look at 3 questions right now on the logarithmic function. As I said, 2 of them are log laws ones, quite basic ones, and then one that is the using the logarithmic scales. So let's get started on our first question so that we can work through it. All right, so our first question is actually quite an easy question when you're using technology. It doesn't look all that easy when we first look at the question, but we're solving for x. So we've got log base 4. We've got 2 to the power of x plus 48, and that's our log, plus 1 equals x. So I'm going to show you 2 methods for solving this question using your graphics calculator. So we'll jump across to the graphics calculator. So I've got the question here on my screen. So we're going to actually use, as I said, 2 methods. So method 1, we're going to use a calculator page, and we're going to use the numerical solve option. Once we've done that, method 2, which you can use either on its own, or you could use as a backup to check your answer, which you should always be checking your answer, and using alternate methods to do that is a great idea. This is going to be using a graphs page and actually looking at graphing the function and finding points of intersection. So I've actually got the question written here on a notes page. So I'm going to insert, first of all, just a calculator page. And in my calculator page, as I said, I'm going to use the numerical solve function. Okay, so with the numerical solve function, you will find that in your menu, and you'll find it under option 3 there, which is algebra, and option 1, so option 3 algebra here, and then option 1 numerical solve. Now with numerical solve, this is a non-CAS calculator, and it will solve questions providing they're not going to end up with an algebraic solution as such. As long as we can get a numerical solution, we can still use our calculator to solve an equation, okay? So what you need to do starts with NSolve, and we need to put that equation in that we had. So our equation was, it's log base 4. Now, the other good thing with this calculator, and this is going to be really important for the next question, I'll talk about it again, but we have the ability to work with logs of any base, which is really nice. A scientific calculator, you can only work base 10 or base E, which is your natural logs, but because we've got a graphics calculator here, in particular the TI-Nspire, we are actually able to work logs of any base. So the calculator allows us to put whatever base we need in there. So I've got log base 4, and it is 2 to the power of x plus 48. That's inside my bracket, so that's the log component. It had plus 1, and it was equal to x. So that's the equation that I need to solve. Now, I need to tell the calculator what it is solving for, because the calculator, remember, it doesn't think for itself. Okay, so we've got to say, well, I want to solve this equation, and I want to solve for x. So I put in a comma, and your comma is down the bottom of your keyboard next to the letter O. So you put in a comma, and then we've got to put in x to say, well, I want to solve this equation for the variable x. I'm going to move outside of my brackets there, press enter, and there's my solution. And that's the question done. Okay, so looking at the question initially, it looks quite complicated. If this question is on your tech active or your calculator allowed part of your test, quite literally, that would be worth 1 mark, because all you've had to do is to place that equation into the calculator, and it's given you your answer. So you're now writing on your question page, x equals 4. Okay? That question could also be put on a non-calculator or a non-tech active, so a tech-free, sorry, that's what I was looking for, a tech-free paper, and it would be worth a lot more marks, because you would have to go through and use your knowledge of exponents as well as quadratics to be able to solve it. Okay, so on a tech active paper or tech allowed paper, 1 mark, maybe 2 for writing down that you've used your calculator and how you've used it. On a non-tech paper, that could be worth 5 or 6 marks. So you need to be aware of that as well. This question could be on either. So that's one method for solving. Now, the other method for solving, if you have any troubles using the numerical solve, another method for solving this one is using the graph application. So I'm going to show you that option as well. So I'm going to add a graphs page here. What I'm actually going to do is to split the question into 2 parts. Okay, so 2 functions. The first function I'm going to graph is going to be the left-hand side of the equation, which is our log base 4, 2 to the power of x plus 48, outside of the bracket plus 1. I'm going to draw that graph. So that's the left-hand equation, left-hand side of the equation. And the right-hand side of the equation, so pressing tab, is just x, so y equals x. So I'm going to press enter there, and we can see that those 2 graphs actually intersect each other. Now, what I'm using here is our knowledge of simultaneous equations, which you learnt back in Unit 1, and also it is actually assumed knowledge. So you should realise that with simultaneous equations, where they intersect is our solution. So I go into menu, I go into analyze graph intersection. I need to put a lower limit, so I can see here that about x equals 3. So just by pressing 3, if you're on a handheld, it's really easy on the computer for me to use my mouse. But I can see that my solution is higher than x equals 3, and all I've done is press 3 and then enter. That gives me my lower boundary, and I can actually already see the solution on my screen there. But if I put my upper boundary at, say, 5, and it's just off the edge of my screen here, you can just see on the right-hand side of my calculator screen, and press enter, and it gives me my intersection here. And again, it's giving me the solution of x equals 4. So we can see there 2 different methods to solve that question, both very easy, both very quick. And again, the question would not be worth a lot of marks, but it is a very simple question, so simple, familiar question when working with your calculator. So that's the first one I wanted to look at. As I said, if it was on a tech-free question, okay, it would be worth a lot more and it would take a lot longer. And what I will actually do is I will provide the working out in the Google Drive for solving this question without a calculator, as well as these 2 solutions here. So this TI-Nspire file will be available to you after the session for you to access as well. Okay, so that's the first question. So while it looked quite difficult, it was actually a very easy question. Something else that I wanted to just make you aware of is you will notice here that on my calculator screen, I've got page 1.1, 1.2, 1.3. Okay, back to page 1.1. That's my question 1. Okay, and so any pages I added after that were linked with that. So this is also referred to as problem 1. So if I was in a test and I was doing this question, I'd have opened up my calculator, decided whether I was using the calculator screen or using the graph screen, and solved that question. What I then recommend you do is to add in a new page to start the next question. Now, the next question is to determine the exact value of the following. Now, we've got here log base 2, 3, multiplied by log base 3, 4, multiplied by log base 4, 5, multiplied by log base 5, 6, and so on, until we get to log base 63 of 64. Now, that looks quite detailed again. Notice, because I've added a new page in, but I actually called it a new problem, notice my page number started at 2, so 2.1 here. To be able to do that, you press Document, Insert, and you choose option 1 there, which is Problem. So if you're not sure how to make the page numbers change so that it's a new problem, it's Document, Insert, and then number 1, Problem. Now, back to our question here. To solve this question, you're actually using the log law, which is referred to as the change of base law. Now, I mentioned earlier that a scientific calculator only works in base 10 and base E. So anybody that's trying to work with logs on a scientific calculator must have their logs in base 10 or in base E. We've got the added ability with the graphics calculator of using any base we like. But to solve this question, you actually need to use this change of base law. Now, the change of base law is looking at how can I solve a log question that is not base 10 or base E. So it works on the fact that if I've got a log of base A and of some number B, I can calculate that using division by doing, just remove that because I hit the wrong button. I forgot to hit Control. I want log base 10, which remember we can just write as log. And I use the b value in my numerator. And then I have log of base 10 and the a value in my denominator. So my base for my original log is in my denominator, and my value for my original log is in my numerator. So using that law, I can rewrite this question, and you'll actually see that it becomes quite an easy question. Now, it's going to take me just a minute to type it, so if you can bear with me. So what I'm going to have, when I rewrite it using this change of base, what I'm actually going to have is log of base 10, 3, divided by log of base 10, 2. And if you want to, you could also use the natural log, so it doesn't have to be base 10, it can be base e. Then I move out of there and I multiply by, and I change the second log. So the second log that was written was log of base 3, 4. So what's going to happen here is I'm going to have log of base 10, 4 in my numerator, and log of base 10, 3 in my denominator. Notice that my numerator of my first fraction and my denominator of my second fraction are the same. So that means they cancel, and it leaves me with log base 10, 4 divided by log base 10, 2. Now, if I continue along with the question, my next fraction is log base 4, 5. So when I put that in, I get log base 10 of 5 divided by log of base 10 of 4. And again, my numerator and the denominator of the following fraction are going to cancel. And that's going to continue all the way along. So we should see a pattern happening here until we get to the end. And then I'm going to have my very last fraction is log of base 10, and my numerator is going to have 64 in it, and my denominator is going to be log of base 10 and 63. So what is actually happening there is each numerator cancels with the following denominator all the way along until we get to our final stage where we cancel everything, and we are then just left with the basic fraction that has a numerator of base 10, 64, and a denominator of base 10, 2. So that entire question actually cancels down to a really simple fraction. And this question, again, could actually be put on a text-free paper using this process and your knowledge then of changing the 64 to become 2 to the power of 6 and then cancelling down. Now, I'm going to use a calculator page here just to make it a little bit easier because I've forgotten that 64 is 2 to the power of 6. But because I've remembered my log laws here, I've simplified it down. I'm going to put a calculator page in. I'm going to add my fraction that I just had. I'm going to show you that it actually works as well with natural log. If I have natural log of 64 in my numerator, and I have natural log of 2 in my denominator, it gives me the answer of 6. Or, as I said, I'm going to show you it's exactly the same if I've got log base 10 of 64 over log base 10 of 2, and the answer is 6. So it's actually a really, really easy question. Again, that would be a simple, familiar question. It may be worth 2 marks, maybe 3. Realistically, your marks are going to be for recognising that you're using the change of base law, for cancelling all of those fractions and recognising that you just need your final numerator, your final denominator, and it cancels down very easily. So this question, again, 2 marks, maybe 3 marks, and the answer comes out at a really easy 6. Okay, so the exact solution for that question is 6. All right, the very last question that I need to do is we're going to look at a modelling question, so a problem-solving question, again using our logarithms. So what we're looking at here is applying our knowledge of logarithms to sound, and in particular it starts talking about octaves. Now, I don't know a lot about music. I like to listen to it, but I cannot play a musical instrument. Okay? I know that we use things such as middle C as the keys, but I don't understand any of that. Okay? However, I'm told here that we can hear frequencies ranging from 30 hertz right through to 16K hertz. Now, the big thing to realise here is that 16K means 16,000. Remember, K as in kilogram, 1,000 grams, kilometres, 1,000 metres, so that K stands for 1,000. That's the first thing you've got to make sure you recognise in the question. All right, it then says, if middle C is defined as 262 hertz, and each octave represents a doubling of the frequency to go to higher pitch notes, or a halving of the frequency to go to lower pitch notes, how many octaves are you able to hear across? So what I've got to do is interpret that information. So the first thing that I do in interpreting that information is say, well, okay, we know that middle C is 262 hertz. So a bit of a rough note taking. If you can imagine, I would be handwriting this, not writing it on my calculator. But I'm starting with 262 hertz. Okay? Now, I can either double the frequency to get my higher pitch notes. So if I double 262, I get 524 hertz. Okay? Or I can halve. So if I halve that, I get 131 hertz. And I can look, typed that wrong, that should be 131. Okay, I'm looking at a pattern here. So if I continue halving, okay, if I halve the 131, I get 60.5 hertz. And if I halve it again, I get 30.25 hertz. Now that's close to my minimum value in my range that I can hear, which is my 30 hertz. And if I go the other direction, as I said, I doubled it, I got 524. If I double it again, I get 1,048 hertz. I'm trying to get this all on one line there for you. Okay, I can see a pattern here. Now that should remind me of using geometric sequences, okay, where I'm starting with 30 hertz and I'm doubling each time. So what I should realise is that I've got a geometric sequence where my first value, my first term, actually T1, is equal to 30, and I've got a known middle value of 262. I've also got a common ratio of 2. So I should remember that term 1 multiplied by r to the power of n is going to give me term n. I should remember that from Unit 1 and my work there. So using that, I've got the first value is 30. I'm going to multiply that by my common ratio, which is 2 to the power of n, and I can get 262. And that can tell me then where that final value is. Or, sorry, how many octaves I've gone up to get 262. So the other thing is I need to know how many octaves have I gone up to get to 16,000. So what I'm actually going to use is 30 multiplied by 2 to the power of n, and I want to know how many octaves I can hear across, is going to give me 16,000. Now, obviously, I'm going to need to rearrange that. And again, I would be handwriting this on my test paper, not typing it on the calculator screen. So, but I need to divide by 30, so I'm going to have 2 to the power of n equals 16,000 divided by 30. Now I've actually got something I can solve. And again, this is where my logarithms come in. So I'm going to go to a calculator page now. And I've got to convert my 2 to the power of n equals 16,000 divided by 30. And so that's going to give me log of base 2. In my bracket here, 16,000 divided by 30. And that tells me it's about 9 octaves. So we can hear across 9 octaves. Now, the other way I could have done that, and I'm going to stay on this calculator page here, you should remember from before numerical solve. So I could actually put in here 30 multiplied by 2 to the power of x equals 16,000. I want to solve for x, and I again get that 9.05. So it's approximately 9 octaves that we can hear across. So there's 2 different ways to solve there, but the important thing is you had to develop that model first. So you had to recognise the pattern. So that's pre-knowledge from Unit 1, your geometric sequences. Recognise that it is a geometric sequence there by doubling, and develop your formula there of your 30 times by 2 to the power of x equals the 16,000, and you can either use numerical solve or you can use your logs, and you're solving there. So it's applying either exponentials or logarithms. You wouldn't get this question on a non-calculator exam simply because you could not get past the log base 2, 16,000 over 30 without a calculator. Okay, so you're going to have that question on a calculator exam, but again, it's a low-level question, so simple, familiar question, but using your calculator. So those are the 3 questions that I wanted to look at today. What I'm going to do now is I'm going to pass over Shelley, and Shelley is going to then take over and look at the differential and integral calculus. So yours, Shelley.
Hi there, can you hear me nice and clear?
Can hear you nice and clear.
Perfect. Hi, Shelley Cross here. I'll be working with some questions on calculus, differential and integral calculus. You'll see on my screen, just checking Mel, you can see the screen well?
Yes, now I can see your screen, Shelley. All over to you.
Perfect. Right, so looking at calculus, we're going to start by looking at some calculus of logarithmic functions and differentiation. So my first question is, you can see on your screen. So what I'll be doing is I'm going to flip between the screen. First I'll discuss solving the question on the screen, and then I'll go to the calculator and we'll look at the calculator application. So here we're looking to find the derivative of the natural log of sine x and state the domain. Now, in solving this question, you'll see I've actually put a solution on the screen. Using the chain rule, I've said let u equal sine x, and using the chain rule, I've managed to solve for the derivative, and I've landed up with sine x, cos x over sine x, which is 1 over tan x. So that shows me the derivative of the natural log of sine x. But in looking at stating the domain, really need to see some sort of visual before I can figure out what the domain is on this particular question. So I'm going to go over now to the calculator. There we are. And assuming you can all see my calculator now nice and clearly. So what I'd like to do on my graph page is I'm going to start by drawing a visual of the original function. So that's going to be f1x, and that would be the natural log. So control natural log of sine x. This is what I'm looking at. So notice I'm in radians, so I'm using my graph in radians. Minus 10 up to plus 10. I haven't been given an interval that I need to look at this graph. So let's change the domain for the moment, and let's say go from minus 2 pi. So I'm going to change that to minus 2 pi. So double click on the minimum value, minus 2 pi. Enter, and I'm going to make the upper value 2 pi. So what I'm looking to see is any patterns within this graph, because in order to look at the domain, I need to know where there are vertical asymptotes, because those are values I'm going to have to eliminate from my domain. So just for the sake of being able to see the graph more clearly, I'm going to make the minimum y value minus 20 and the maximum y value 20. So it looks pretty much to me like there is a vertical asymptote at minus 2 pi, another one at minus pi, at 0, and at pi. So this graph is my original function. What I need to do now is look at my derivative function. So hit tab to add a new graph. Now, because I want to connect these two, I want to find the derivative of my graph of f1. I'm going to use my template and the derivative, and I want the derivative in terms of x, and my original graph was f1x. Now I have a picture which shows me of the original function and the derivative function, so I can quite clearly see that the derivative function has got a vertical asymptote at minus 2 pi, pi, 0, and pi. So for my domain, I would need to eliminate those values using plus k pi. So I think it's always very good to have a look at your graphs and to visualize what you're looking at, because in looking at this question at face value, I'm just going to pop back to the PowerPoint now. Got like that, there we go. To work out the domain without actually having a picture in front of you is pretty difficult in this case. I'm actually just going to pop back to my software. To double check my graph, it's another very good idea to add in the derivative that I found out, which is the graph 1 over tan. And that confirms for me that what I've actually done numerically on paper is the same as what I've found using the calculator. So that is a very nice double check. For my next question, question 5, in any of these questions, as Mel mentioned earlier, it's always a great idea to start each question with a new problem. So I'm just going to go menu, doc, insert, and I'll insert a new problem for my next question. And in my next question, I'll also be using a graphs page. So let's go back to look at the question. So question 5, I've been given a cubic function, given f of x equals x minus 1, x plus 1, x minus c, where c is greater than 1. We've been told the tangent is drawn midway between the leftmost x-intercepts of f of x. If the tangent crosses the x-axis at x equals 3, determine the value of c. Right, so to try and unpack this question, the first thing I'm going to do is highlight the fact that c is greater than 1. I've drawn a bit of a sketch for myself so I can see that f of x, x minus 1, x plus 1, so two of these roots are minus 1, x minus c, because c is greater than 1, I know that c is somewhere towards the right-hand side of positive 1 on my x-axis. The next thing I know is that the tangent is drawn midway between the leftmost x-intercepts. So the leftmost x-intercepts are minus 1 and plus 1. Midway between minus 1 and plus 1 is where x is 0. So that's another clue that tells me something about this question that I need to remember in a moment. So what I've drawn is I've put a little sketch of my graph. I know it's a cubic function. I know it's the value of a in my cubic function. If I expand, the brackets will be 1. So I know its general shape is going to be increasing, decreasing, and then increasing. And I've written down, I've shown on my graph that the third 0 is at C. What else I know about this graph is that there is a tangent when x is 0. So I've established that midway between minus 1 and 1 is where x is 0. So my tangent is drawn when x is 0. To find that value when x is 0, substitute into the original function, and you'll find that when x is 0, the y-intercept there is c. So, where to go from there? So I know that my tangent now must pass through 3, 0 on the x-axis. I know that it starts at, is one of the points that it crosses the graph is at 0, c. So I can find the gradient using the gradient formula, y2 minus y1 over x2 minus x1. And I know that somewhere there needs to be a tangent that passes through here. Now, it's pretty easy to do this with trial and error on the calculator, and I'll show you that in a moment. But in order to make sense of that, I think it's a good idea to have a look at the mathematics behind what we're looking at. So what I've done next is I've expanded. I've said f of x is equal to, and I've expanded my brackets, I've differentiated, and I've actually found out that my value for c is 3, and my gradient is going to be minus 1. Let's hop back to the calculator now and have a look and see how that works. So there's a few tools on graphing on the calculator that are really important just to be totally familiar with. So I'm going to start by looking at this graph. It's the graph of x minus 1, x plus 1, and then x minus c. So I don't know the value of c, but I know that it needs to be bigger than 1, so I'm going to just guess maybe 2. So I'm using trial and error, and I've drawn my graph here. Let's put some values on this graph. So the first thing I want to do is I want to put some points on the graph to establish the values that I need to know. So I'm going to do menu, geometry, points and lines, point on, tap the graph once, tap the graph twice, and escape. I actually want that value, the x value of that point, to be 0. So double click on the x value and type 0. And straight away I can see that the midpoint between -1 and 1 is where x is 0 and y happens to be 2. Now I'm going to draw a tangent at that point. So menu, geometry, points and lines, tangent, and I know my tangent needs to go from that point. And I grab the end of the tangent and just make it longer. So I can see there that it appears as if my y-intercept is 0 and my tangent goes through the point x plus 2. We were told that the tangent needed to go through the point 3 on the x-axis. So let's change these values. What I know is x needs to be greater than, c needs to be greater than 1. So let's try 4. If I try 4, I can see that my graph actually goes through the point plus 4. So it looks like there's a bit of a pattern here. If I change that to be 5, my tangent is going through the point x equals 5. I was told it needs to go through the point x equals 3. So clearly, it suggests that this value needs to be 3. My equation of the tangent then is y equals minus x plus 3, which is the same as what I actually found out analytically through my explanation earlier. So that's pretty cool. Now let's look at question 6. So question 6 is an integral question. So we're looking at some integration. And it's an interesting question because it approaches the whole notion of area from a slightly different perspective. So we've been given f of x, the integral of f of x dx from 0 to 4 is 12, and we have to determine the value of 2f of x plus 1 dx. So again, what I've done is I've written the mathematical justification on the PowerPoint, and then we'll look at, well, maybe we can, no, we'll go through the justification on the PowerPoint. I'm going to flip to this page quickly. Really, let me go through it. We know f of x dx, the area between 0 and 4 is 12. So in looking at 2f of x plus 1, I can take the 2 out to the front, bring it in front of the integral sign, and essentially I've got twice f of x from 0 to 4, which I can substitute for 12. The integral of 1 is x, and the answer then is 28. Essentially, this f of x dx is just an unknown. So if we treat that as an unknown, for example, p, we can do that on the calculator really, really quickly. So I'm going to insert a new, sorry, not that, doc, insert a new problem. And in this case, I'm adding a calculator. I knew that I've decided I'm going to call my unknown p. So let's use the template integral. My interval is from 0 to 4. Let's call it p because it's just an unknown. Oh, I want to solve this actually. So dx. I'm trying to solve this equation. Sorry, I should have started out with this. Algebra numerical solve is equal to 12, and I'm solving for p. And it tells me that the value of that unknown is actually 3. Let's now use the same tool again, the integral tool. And now I want to go from 0 to 4. Well, my unknown is 3, and I want 2f of x plus 1. So I've just got 2 times 3 plus 1 here. And on to 28. Exactly what I got. Showing my working out pen on paper. So that's the 6 questions that Mel and I were going to do with you. Thanks very much for attending. If you'd like to see any more questions, check out the student blog, which you would have got information for in the PowerPoint at the start of your invitation to the webinar. Thanks very much.